let's talk about the difference between fluorescence and phosphorescence. We know that fluorescence and phosphorescence are both basically photoluminescence. So before going to talk about the fluorescence and phosphorescence, let's know about what is photoluminescence. We know that basically photoluminescence is the inverse of absorbance. When we have a molecule and when we shine light, use visible light or ultraviolet light, so the molecule absorbs light and the electrons in the molecules are excited from lower state to the higher state. That lower state we call a valence band and the higher state we call conduction band, or we call HOMO and LOMO, right? So the peak we can see here, it is basically the light absorbed by the molecules. So it gives us this peak. Now I explained in my first video that the photoluminescence peak are shifted to the higher wavelength. So this blue peak is fluorescence and this black is phosphorescence. Now we can see the shift in wavelength, and this shift we call Stokes shift. Why this shift occur and how we will know that this peak is from fluorescence and this peak is from phosphorescence. So in this video I will make it very easy. So let's get started. This we know that this is the ground state. Let's suppose that we have two electrons in orbitals. So we know that one electron is spin up and another electron is spin down, right? Now what will happen when we shine light? So due to this light we will excite electron from the ground state to the excited state. Now we can see that this electrons does not change the direction orientation of the spin. So it is exactly the same it was before, but it just excited to higher state. Now basically what will happen, this electron will do now some vibrational relaxation or some internal conversion, because this is the first excited state, this is the second excited state, this is the third, this is the fourth, this is the fifth, for instance. So previously our electron was here, now this electron jumped from that to this one, and this is vibrational relaxation, or this we call internal conversion. So due to these two phenomena, this electron dissipate heat. In that heat maybe convert to the neighboring molecule or something. So this electron lose some energy, and this process is called non-radiative transitions, because when electron jump from here to this portion, there is no light emission here. There is no light emission. This is why we call it non-radiative transitions. The transitions are there. It is understood from higher excited state to the lower excited state, but there is no radiations, right? When the electron finally reach to the lowest excited state, then what basically happened? It dropped to the ground state, and due to this we get light, and this is basically called photoluminescence, and this kind we call fluorescence. This fluorescence, how we know that this is this phenomenon is called fluorescence? Okay, I will explain this. This means that when there is very short time, so this we call fluorescence, because in both cases we get the light of longer wavelength. So in case of fluorescence we know less longer wavelength. In the case of fluorescence we get longer, the longest you can call the wavelength. But how we will know that this is basically from fluorescence or the next one is from phosphorescence? Because in both cases we get longer wavelength. So how we will differentiate that the material is fluorescent material or the material is phosphorescent material? So I explain. How I explain that when we switch up this light, and this emission will also switch automatically. So we can know that this material is fluorescent material. For example, there is a continuous source of ultraviolet. This is ultraviolet. We are sending ultraviolet, and we know ultraviolet has a shorter wavelength. So when we are bombarding here the ultraviolet, and when this electron come down to the ground state, it emit visible light. We know visible is less energetic, so we mean high wavelength. So this is the best example of the fluorescence. But it can also the case of phosphorescence. Then how we will differentiate? For example, if you bombard a UV light on phosphorescent material, it will also give the visible light, because in that case also we have longer wavelength. But the difference is the time. In the case of fluorescent material, when we switch up the source of this ultraviolet radiation, for instance, so automatically the visible light will disappear. Right? This is the common example of the fluorescence material. Now let's discuss the phosphorescence phenomena, or we call the phosphorescent material. Right? For example, when we shine light here, we shine light. Due to this light, we send electron from ground state to the higher state. Now, so far we have the spin orientation is okay, it's not changed, and this electron may cause some vibrational relaxation in some internal conversions. But there is another phenomena, and that we call inter-system crossing. You can see inside the system they cross something here. The electron comes from here to there, and when it reach here, this electron change the spin direction. Look now, you see here, this is this we call basically the triplet state. In the first case it was called the singlet state. So it changed the orientation. So there is a rule of multiplicity that is called 2s plus 1. So if you look here, in this case both spin are adding here, so the spin is basically 1. So 2 multiplied by 1 plus 1, so it gives us 3 here. This is why it is called triplet state. It gives us 3, right, in this case. But if you look into the first case, so the 2s plus 1 basically gives us 1. Why? Because the spin is 0 in the first case. Because the spin orientation does not change when the electron jump from lower state to a higher state. So s is basically 0, so it gives us 1. This is called singlet state, right? But in this case it is called triplet state, right? So when we shine light here, the electron have done some relaxation, vibration, internal conversion, and then electron done something very important, that is inter-system crossing. Crossing means it cross some boundaries here and enter the system, not outer system. Now, and it also changed the orientation of the spin, this flip spin. This is another story why it flip, in how it flip the spin, but just for the sake of this time, you just need to have just in mind that in inter-system crossing, the electron change the spin, it flips the spin, right? So the net spin is now 1. Now this electron will now come here and it will emit very longer wavelength, and this phenomena we call phosphorescence. To make it simple, the difference between the fluorescence and the phosphorescence. Simple mean if it disappear immediately, so you call this is the fluorescence. F come first, P come later. So you can also differentiate this in this way, that when it disappear quickly, fluorescence means emission of light. Like when something is glowing at home, when you feeding continuous ultraviolet and it convert to different colors, red, blue, green, etc. So when you switch off the UV light, the visible light, the green, blue, etc. will switch off automatically. This is called fluorescence automatically. While if it remain for some time, so this is called phosphorescence, right? And fluorescent material basically is explained. The emission is basically immediate stuff, right? But it the phosphorescent material stores some absorb light. And as we explained that here, if you look into this first graph here, the first graph, it shows basically here look, the fluorescence basically, the wavelength is longer than the absorbance but shorter than the phosphorescence. Why? In phosphorescence, there are so many phenomena. So the electron lost most of energy because it has done a vibrational relaxation, internal conversion, and additional inter-system crossing. So electron lost a lot of energy, and finally it has very small energy. So if we have small energy, so look these equations, we have very long wavelength here. So the phosphorescence energy is very less as compared to the absorb photons, and while the fluorescence is also less energy than the absorbed photons, right? But in case of fluorescence, we have less dissipation of energy, but in case of phosphorescence, we have a lot of dissipation and a lot of heat is there. So we lost most of energy and we just left with a small amount of energy. This is why it has a very long wavelength, right? So this was all about the fluorescence and phosphorescence. I hope it is very clear that how we will know that the material is fluorescent or phosphorescent. As I explained, that when the emission stops abruptly when we switch off the source, so this is a fluorescent material. When the material is still glow after switching off the source light, so you can call this is a phosphorescent material. Thanks for watching.